Okay, so in today's lab we're going to discuss fluids. Basically some sort of understanding about pressure, and then we'll follow it up with another lab on the buoyant forces, yeah, buoyancy and all of that. So over here in this particular one moment, yeah. So you see that there is a couple of things. On the left hand side, I'm going to call these configurations. Yeah, there are three configurations. We'll just look at a couple of them. Right now, this is a configuration we'll use. By configuration, I mean the shape will change. Yeah, the shape of this vessel or this tank, that would change. You can see a small snapshot of that here. Yeah, see. So there are many things you can play around with. We'll use this one and the second one for this current lab. This top tap is an inflow control. Yeah, I can increase it. And this bottom tab lets the water out. Okay, that's what these two controls do. There are a couple of displays. I'm going to click on grid and ruler. This grid basically just, yeah, as you can see, just tells me the height, and the ruler measures the depth. Okay, cool. You guys have understood all the controls so far? All right. So now all I'm doing is I'm just expanding these different plus signs. So one of them says fluid density. Now remember, the density of water was 1 kilogram per liter. When expressed in standard units, that would be 1000 kilogram per meter cube. This we have already done in class, but if you guys have any doubts in this, go back to the basics and figure this out, okay? But this is the density of water itself. And this is the gravity, the actual force of gravity, I mean acceleration due to gravity is 9.8 meter per second square. For our convenience, we are going to use 10. In our calculation so far, we've used 10. So now again, we will stick to 10. All right? Everyone okay so far? Okay. So now there's another extra thing over here. You see that it says pressure. And the units, these are the units of pressure, okay? Units, this metric, atmosphere in English. So we'll stick to metric units. Metric means the standard units where we use pascals, kilograms, meters, seconds, and all of that. So I can drag this pressure gauge out, okay, to check the pressure. See, anywhere at this particular height, where this is there, it says it's 103.367. If I go up or low, this pressure changes. Does that make sense, or is that confusing you? Why would the pressure change if I'm moving it up and down? Any ideas? You guys can type out your answers. Why you think the pressure is changing when I'm moving it up and down? Okay. I would take the second answer, what Ashna said. There is more or less air above it. Exactly, Sneha, that's the simplest thing. Yeah, more volume, more amount of air. That's the easiest answer. The thinner bit is a little complicated, but that's the thinner bit is a little bit complicated. Yeah, Arjun. Yeah, what you're speaking about is an interesting observation, but that's not what we're talking about. We assume that there's the same amount of air everywhere. Okay, that's our assumption because we are talking about height very close to Earth. Okay, so because there's more air at the bottom compared to this height, so the pressure changes. All right, as simple as that. Cool. Also, the reading is 103.367 kilopascal at this level. Now, the actual reading should be this, yeah, 101.325. That's the actual atmospheric pressure. But you see that it's slightly higher here. Why do you think that is? Why is the atmospheric pressure showing to be this value? Why is it showing to be 0.367? I'm just covering the basic before we go on and do the simulation. It's a really simple simulation, but you guys must know what we are doing. Humidity, very interesting. No, not because of humidity, but I like the train of thought. It's very simple. It's a lot simpler than what Sneha just said. And the answers on this itself. No. I'm not talking about above or below. Viewer 6, also known as Arjun Nair. I'm not talking about air above or below. At this point, I'm saying that theoretically it should be 325. Exactly. Very well done. The gravity, the acceleration due to gravity is 10. The actual acceleration, I changed it. It's supposed to be 9.8, but I changed it to 10. which means that there is a stronger pull downwards, and hence the pressure has increased. Even by, although by a small amount, but it's definitely increased. Okay? Is everyone okay with this? Yeah? So, what we just did is analyzed the problem, so to speak, yeah, or the numerical or something thrown at you. You may not always have standard conditions. Things may change. You may have a situation where someone tells you that, hey, the gravity on the moon is 1/5 that of Earth, and then do calculations over there. So don't get scared if that happens. Just go back to the basics and do this. Yeah, what we just did. Analyze everything step by step, right down to the basics. All right. Now let's lower this pressure gauge into this tank. There is some water, some random water. So you can see that it's increasing. Okay, and as soon as I put it in water, the increase is a lot more. Can you guys explain this? Why did it start increasing so quickly? Like all over from the top point till the bottom point, it's just moved less than 1 point. Yeah, it's gone from 103.36 to 103.4. Yeah, so that's something like a 0.1 increase or 0.05 increase. But as soon as I go inside, it's increasing very, very quickly. Why did that happen? Water is heavier, density changes. Exactly. Good stuff. So you guys are all on the same page. Remember, pressure was given by the equation H into rho into G, the key factor being density. Well, obviously the density of air is a lot lower. Density of air is just like 1.2 kilograms per meter cube, but there's a very, very large height of air. So that causes this change in this upper part of this simulation. As soon as you get into the water, the increase is a lot more because, well, the density of water is 1,000 times that of air, almost 1,000 times. Yeah, like something like 900 times or something like that. Okay? This is clear? These ideas are clear? Is everyone okay with this? Okay, now I'm going to empty the entire water and let's just see what happens. Yeah, we've emptied the whole water tank. I'm going to measure the pressure at these different heights. Let's take 2 meters for example. It says that it's 103.417. Okay. Now, if I move this pressure gauge up and down, it changed. Yeah, the value changed as we saw. Now, if I move it horizontally, do you guys think the pressure value would change? Okay, some of you are saying no. Everyone's saying no. Let's see. Let's see if that's true. Okay, more or less completely horizontal, and yes, you guys are correct. It does not change. Excellent, because the pressure only depends on the height of the stuff above it. The stuff, by stuff I mean liquid, solid, whatever. At this point, we'll just talk about fluids, not solids. We'll just talk about fluids at this point. Okay. So pressure increase only with the height of the air column, or if you fill in water, then height of water. Now, it's amazing that you guys have figured that out. Let's. This is where I want you to note things down. Yeah. At this point, at the 2 meter level, the pressure is 103.417. Yeah, please make a note of that. Okay? Let me know when you're done. Yeah, you've noted this value? Okay. Now, I'm going to go to a depth of 3 meters. Let's note this value down. Yeah, it's 103.429 here. I'm sorry, it's 43, right? 430. Let's be accurate if you can. Yeah. 103.430. Cool? Now, what is the difference in pressure between the 2 meter line and 3 meter line? Subtract those two values. What is the difference? Yeah, guys. 0.013, not point. Come on, it's just subtraction. Okay, cool. 0.013. Okay, that's okay. Not an issue. Now, note the 2 meter line. It was 103.417. You have that. What is the difference between this and the 1 meter value? 1 meter value is 103.405. What's the difference between these two now? 0.012, and the difference between this 0 meter line and 1 meter line, can you guys do this now? 103.393 minus this. Exactly. So it seems like the value is something like 0.012, 0.013 throughout. Yeah. If I change this is going to happen only if we assume that there's same amount of air everywhere. Yeah, that the air does not become thinner. So we are not talking about very high up in the atmosphere. We're just talking about things close to the surface of the earth. Yeah, within like 10-15 meters. Okay, or maybe even 20-30 meters above the earth's atmosphere, it's going to be the same. Only after 50 meters do you start noticing the difference. Yeah, that it becomes really thin. Okay, that out of the way. So it seems like for every increase of 1 meter of height, the increase in pressure is 0.012 kilopascal or 12 pascal. Does that make sense? This 12 pascal business? Let's see. I'm going to pause this simulation. So I'm going to add water up to the 2 meter mark, which is I'm going to be adding 1 meter of water. Okay? Let's do that right away. Cool. I've added the water. Now, what you see is that the pressure at the 2 meter mark would be the same as the atmospheric pressure, right? Which is like 103.417. That's what we measured. That's okay. So please write this down. Write this one down. Let me know when you're done writing this. Okay. Now, when I take this pressure down to at the bottom of this, whatchamacallit, I don't think I read the full water. One moment. Oops, sorry. Okay. At the bottom of this now it's 113.4 kilopascal. Okay. At the 3 meter mark, I've added 1 meter of water. Can you write this down, please? Now let's go back to the class and let's calculate and see if this value makes sense. There are a couple of things that are interesting and that are important. I'll talk about it in class. Yeah? So to reiterate, I told you guys that we did a calculation that explained this 0.012 kilopascal or 12 pascal increase in air. Yeah, when you go from 1 meter from this point to this point, there's an increase in 12 pascal. That's because, well, the density of air is approximately 1.2 kilogram per meter cube, and you plug that value into rho gh, and you get 12 pascal. Similarly, we did a similar calculation where we added the pressure due to water, and we subtracted the pressure due to air because water occupies the space that was occupied by air. Alright? And hence this calculation is good. Now, if I increase the watermark, if I increase the amount of water now to say the 1 meter mark. Just give me a moment while I do that. Okay, I have done that. Now the pressure has increased to 123.4. Alright? Do a quick calculation and let me know if you're okay with this. Yeah, I would be adding twice the pressure due to water, which is simply 10 kilopascal, and I would be subtracting twice the pressure due to air. I'm talking about 1 meter of stuff, okay? 1 meter of water would have a pressure of 10 per kilopascal, which we have already derived, and 1 meter of air would have a pressure of 12 pascal, not kilopascal, just pascal, which would make it 0.012. Do you guys understand this, or do you want to go back to the class and you want me to do this working? Which one would you prefer? No? Is this okay? This verbal explanation is okay? What about the rest of you? If anyone has any issues, let me know. This is alright? Sneha? Did not get a response from you? Okay, great. Excellent. Cool. Then we can move on. So, so this is a good way of checking if what you have done, this experiment or the simulation makes sense or not. Now, let's keep everything else constant. I'm just going to change the configuration to the second setting. Okay? You see that it has a funky design. It's got a weird whatchamacallit, a partition in the middle and all of that. Now let's verify if the pressure is the same. Before I do that, I'm going to drain this of the whole water, okay? And I'm going to add water again, but I'm just going to drain this water so that you can check the pressures. So at the bottom, remember it was exactly 103.43. You guys have these values written down, right? Please check and tell me if this is okay. Right at the bottom, okay? And again, at the 2 meter mark, 103.417. That also seems to check out. So yeah, the pressure is the same. Now I'm going to add water. Say to the 1 meter mark. Yeah. Now let's see the pressure. Pretty interesting stuff. The pressure is exactly the same, irrespective of this partition business. What does this tell us? Although there is some sort of a, just above the outlet pipe, very little height of water is actually there. What causes the pressure to be same is that both these containers are connected and hence the heights are the same, which means the pressure would be the same whether I look at it over here or even if I look at just above this outlet pipe. Is this okay? That the shape of the reservoir is unimportant. What is important is the vertical height of the water column. No, volume does not matter. Exactly. It's just the height. Remember, that's exactly why I told you guys, showed you that thing. Yeah, if I move this pressure horizontally, it doesn't change. Now it's changing because I'm not moving it exactly horizontally. If I move it really slowly and at the same height, it stays at 123.1. Yeah, if I do it carefully, which is a little difficult to do with a mouse. You can do it easily with maybe a scale or something. Yeah. So this means to say hydraulic system. Yeah, hydraulic basically means anything to do with water. So this is the basic idea of fluid dynamics and stuff. Okay, and this is why is this is because of gravity, because there is only one force. Yeah, if gravity acted in other directions, then sure you would have pressure in other directions. Not pressure in other directions, pressure would change. So the concept behind hydraulic system is a little more complicated because there pressures would change all around the place because there is movement, there is actual movement of fluid. So don't worry about that. We're talking about static fluids, yeah, not really moving fluids at this point. Okay? Cool? Is everyone okay with this? So that's why I showed you guys that horizontally does not change, only vertically the pressure changes. This means that the volume doesn't matter, it's only the height that matters. Alright? So now let's the pressure is exactly the same as before, which we already ascertained. Now what else is there over here? Just one moment. Oh yeah, that was it about this simulation. You can mess around with the third configuration as well. Yeah, I'll give you the link to this. You can do many funny things. This actually a little more complicated, but we won't look at the third configuration. We'll just look at the second and the first. Okay? And you guys can play around with it later as well. So that was it about this part of the simulation. Just hold on, let me start up the second. Okay, cool. So I'll just recap that for the recording. So yeah, the left hand side is the properties control. We have selected my block. Right hand side is the blocks, the type of blocks. We've chosen a custom block so that we can figure out things according to what we want. The bottom right that shows 100 liters is simply the measure of the tank volume, and it shows to be 100 liters. Now everything else remaining the same. I'm just going to reduce this weight to the least possible value, which is 1 kilogram. And you can see at the bottom there's a density. Now I won't mess with the volume. I'll let the volume be 5 liters. What I will do is I will increase the mass of this block, which in turn would increase the density because I'm keeping the volume constant. Is this okay, guys? And if I increase the mass keeping the volume constant, the density would automatically increase. Yes? Okay, cool, excellent. So notice, keep a look at two things: this liter business and also the actual physical movement of the block. So let me increase the mass of this block. Mass does not, why does mass not matter? Actually, mass is matter. But, just kidding. But what do you mean by mass does not matter? Arjun Nair? Very interesting. Okay, okay. The volume of body displaces. Okay, sure. But the density matters. Would you agree with that? What would decide the volume of the water displaced by the body? You're jumping a couple of steps ahead because you've already done this in class. That's fine. But hold on to those ideas. You'll see now why mass matters. In mass, I agree, does not matter. But density matters. Is that okay? Arjun Nair, is that okay? The density would matter? Alright. That's what I was going to prove to you guys, but hey, you stole my thunder. But that's alright. It's excellent that you have figured this out. Is this okay with everybody else? What he just said, what Arjun Nair just said. Did you guys follow that? It's the ratio of the mass to volume that matters, which is the density. Okay? So now when I increase the mass of this body, you can see that the volume that is submerged keeps increasing. Pretty cool, right? Yeah. Volume submerged increases, and hence obviously the volume of the entire thing increases. Yeah. 100 liters plus 2.4 liters, which is the volume of the block that's submerged. Now, it keeps being submerged. That means at some point it's going to sink. Let's see what that point is. Okay, it's almost sunk. It's like just 0.87. Okay, let me go to the density of ice. Density of ice. This is the density of ice. Yeah, 0.91 kilogram per liter is the density of ice. 1/10 of the ice block is outside and the rest of it is inside. So now let me increase this density further, a little bit further. As soon as I hit 1 kilogram per liter, I go past 1 kilogram per liter, it sinks. I go back, it starts floating. Pretty cool, right? So, what is happening at this 1 kilogram per liter? Why is this important? You know, why is that the magic number? Any ideas? What's the deal with that? Density of water. Exactly. It becomes denser than water. Alright? So, since the volume of the block is 5 liters and the mass is 5 kilograms, for a density of that would mean a density of 1 kilogram per liter would be exactly equal. Now I've increased the mass to 5.01. See, I've increased the mass to just this much. Even then the block sinks. Do you guys see that? So even if it's slightly just above the density of water, it would sink. That was a good example to show you guys that. Let's go back to class just for a moment. A small little bit of calculation is what we are going to do. Just hold on. So clearly, if the mass of the block exceeds 5 kilograms, the force of buoyancy is lesser than its weight, and hence it sinks. Okay, there are essentially two forces acting here. One is the weight of the body, which acts on itself, and also the force of buoyancy, which acts upwards. So if the weight is greater than the buoyant force, it would simply sink. Is this clear, guys? Just a revision of things you've done in class already. Okay. If the maximum force of buoyancy is greater than the weight of the block, what happens? Let's drag this weight out, and I'm going to change it to say, hold on, one moment. Yeah, I'm going to change it to 1 liter. Sorry, 1 kilogram, exactly 1 kilogram. So I drag it out and dump it back in. Okay, I've just made sure that it's the lowest setting, and the volume reading of the tank in water, water in the tank is 100 liters. As soon as I drop this down, it starts, after it stabilizes, the volume is exactly 101 liters. Yes? Agreed? Now if I take this block and I drag it all the way down, the volume has increased to 105 liters. That makes sense because the volume has increased by 5 liters. The volume of the box is 5 liters. Okay? Now, the weight of the block happens to be only 10 Newton. That's the weight of the block that's actually submerged. Hence, the volume now is only 101 liters. Does that make sense, guys? This means that the buoyant force is only 10 newtons. It could be 50, but it's only 10 at this point. Cool? Why? Because it's displaced only 1 liter. Easy enough, right? Okay. So I've just used the formula that the new force of buoyancy should be equal to the weight of water displaced, and the weight of the water displaced is clearly 10 Newton because the density is 1000 and gravitational acceleration is 10 and the volume is 1 liter, which is 10 power minus 3 meter cube. Okay? Was that verbal explanation okay, or do you want to see written step-by-step thing? Let me know, this is extremely important. If you guys want me to write it down, I will do so. I felt that this is easy, which is why I'm saying it verbally. Is this clear? Or would you prefer to see a working? Ashna says it's clear. Isn't the weight of water displaced 0.2 into 10? Why is it 0.2, Arjun? Hold on, wait. Hold on. Let me look at the first question first. Sometimes if you drop something from a high enough position, it gets submerged and it comes back up. Exactly. So that's what happened, no, here. That's what happened. If I drop it from a high position, it gets submerged and comes back up. The reason why it gets submerged is because of inertia. Okay, it's going down, it has a high acceleration, and then suddenly it says, hey, water wants to push it back up. And it does that. So very, very good observation. And Arjun, the weight of the water displaced is not 0.2 into 10, it is 1 into 10. The density that you're using is the density of the solid, which is not correct. It's supposed to be the density of the liquid or the fluid that you use. Is that okay? If you want to use a formula directly, that's the direct formula. I've explained to you conceptually how it is just 10 newtons. Because only 1 liter water is displaced, and since water is displaced, its density is 1 kilogram per liter. Yeah, makes sense, Arjun? And everybody else as well? So in this case, the weight of the body, which is 1 kilogram or 10 newtons, is exactly balanced by the buoyant force. So there's some sort of an equilibrium, yeah? Both forces are equal and the block stays afloat. Now if I increase this mass to 2 kilograms, what's going to happen? What do you guys think is going to happen? It will sink a little, density increase. How much will it sink? Can you guys tell me how much it would sink? Now that we are doing the math bit of it, then you guys, what's the new weight of the block going to be? It will clearly be 20 newtons, right? 2 kilograms into yeah, exactly. The new weight will be 20 newtons. So how much water would be displaced? 2/5 of the block would sink. Okay, I accept that 2/5 would sink. So what would that mean? How much? What would be the final volume of the tank? Exactly, 102 liters. Yes, 2/5 of the block would sink. Excellent. That's exactly what allows you to come to that conclusion. Yeah. See, what you guys said is absolutely correct. So now notice that the force of buoyancy has increased to 20 newtons. All right. So the force of buoyancy depends on the volume of the water displaced or the fluid displaced by the solid, which is basically Archimedes' principle. Agreed? Okay, excellent. Now if I change this to 4 kilograms, clearly it will sink to 4/5 of its volume, which is like 4 kilos, and the total volume is 4 liters. Understood? Are the ideas clear? Okay, that was it about the simulation. Let's get back to class and we'll try and understand these ideas in detail. what we've done so far. Just give me a moment.